Welcome to problem solving session for linear algebra. I am Siddhi Balu Amburi from IIT Gandhinagar, and today we will discuss problems related to syllabus from week 8, that is problems related to characteristic polynomial, diagonalizability, multiplicity of eigenvalues, and invariant subspaces. Okay, so we will start with our first problem. So question 1, that let T be a linear operator on a finite dimensional vector space V of dimension n. So T is linear operator from V to V with n greater than equal to 2, and they are saying that recall that the eigenspace E lambda corresponding to an eigenvalue lambda is the subspace null space of T minus lambda I. And we have to check whether the following statements are true or false. So first statement is that if T has exactly n distinct eigenvalues, then T is not diagonalizable. So any guesses here that they are saying that T has exactly n distinct eigenvalues. So T is a map from V to V where V is n-dimensional vector space, and they are saying that T has n distinct eigenvalues. And if T has n distinct eigenvalues, then T is not diagonalizable. Any guesses?
It should be diagonalizable.
It should be diagonalizable. So this statement is actually false. So we can just take this, since n is greater than 2, we can just take this I identity V going to V, or let me just write explicitly that x comma y going to x comma y. Then T of 1 comma 0 is 1 comma 0, and T of 0 comma 1 is 0 comma 1. Then with respect to standard basis, so beta is this 1 0 0 1. Then T beta beta is 1001, which is diagonalizable. Okay, and other way to say that these are, if I am to write, these are eigenvectors 1 into 0 comma 1, and they are linearly independent, and T is from so I is from R2 to R2, and there are the base of R2 is spanned by these two vectors. So beta is a set of eigenvectors, which is forming a base for V. So this is diagonalizable. This is also one equivalence to say that something is diagonalizable or not. Okay, so this statement is false. Okay, so let us move to our second statement, that if T has n distinct eigenvalues, then now they are saying that T is diagonalizable. And as sir suggested earlier, that this statement is true, that if T has n distinct eigenvalues, then T will be diagonalizable. Why? Because we have proved this theorem in the lecture, that let T be a linear operator on a finite dimensional vector space V of dimension n. If lambda 1 to lambda k are eigenvalues of T are distinct, and suppose that V1 to Vk are corresponding eigenvectors, then this set V1 to Vk is linearly independent. Okay, so this statement we have. So now what they are saying, that T has n distinct eigenvalues. So T has n distinct eigenvalues. So since T has n distinct eigenvalues, this implies that say lambda 1 to lambda n, then by above theorem, what we will have is that this set V1 to Vk, Vn of corresponding eigenvectors will be linearly independent. And then it will form, this implies that this set V1 to Vk forms basis. Basis for V. Therefore, T is diagonalizable. So this is one of the definition of something being diagonalizable. So if all the eigenvectors, and if they form basis for V, so if T is from V to V and all the eigenvectors forms basis for V, then T is diagonalizable. Okay, so from using this theorem, so here they were talking about k distinct eigenvalues, but we are already given that for this question they have given that there are n distinct eigenvalues for our T. So corresponding eigenvectors will also be form a linearly independent set. So V is finite dimensional of dimension n. So then this set V1 to Vn forms a basis. So linearly independent set of cardinality equal to dimension forms a basis for vector space. So we are using that property, and this will give that T is diagonalizable. Any doubts here? Okay. Third is that if lambda is an, so this statement is true. If lambda is an eigenvalue of a linear operator T, then E lambda is a T invariant subspace. Okay, so what T invariant subspace means? So if T is from V to V, then W subspace of V, or a subspace W of V, is called T invariant if T of W is again contained in W. So T of W means what? It is T of W such that W in W. The set of all images of W under T. So this is the definition of T invariant subspace. So what E lambda is? So E lambda is all these V such that TV is equal to lambda V, right? Okay, so this is the definition, or this is also null space of T minus lambda I, and so on. So if we consider this that it is V such that TV is equal to lambda V, then let V belongs to E lambda. Then I need to apply T on this, and then whether I need to check whether that element again belongs to E lambda or not. So V is in E lambda. So T of V is what? It is lambda V. Okay, so I need to now check whether this lambda V is in E lambda or not. Okay, so how will I conclude that lambda V is in E lambda? So what are elements of E lambda? That T of V is equal to lambda of V. So what I need to check that this T of lambda V must be lambda of V. Okay, so if this happens, to show that T of lambda V is lambda into V. So what is T of lambda V? It is lambda into T of V because T is linear map. So it is lambda into lambda V because TV was lambda V anyway here. So this is lambda square V as we needed. Okay. So therefore what we get that this V is in lambda V. When I apply T on this, that for V in E lambda, T of V which was lambda V, this belongs to E lambda. So therefore T of E, since this was true for any V in E lambda, we get this thing. Okay. So therefore E lambda becomes T invariant subspace. Any doubts here?
Ma'am, can we say that eigenspace is the set of all the eigenvectors?
Yes,
Of
definitely. This is the definition of eigenvectors, right? Corresponding to lambda. So exactly.
So whether eigenspace is a vector space?
Eigenspace will be subspace, sir. Yes.
Means whether eigenspace will qualify all the properties of a vector space?
Yes, it will. That's why it is subspace, right? Because anyway, when we started with E lambda, we already assumed that E lambda is a subspace of V.
No, in generally, otherwise, whether if I have a diagonalizable
Okay.
match, so I have only three eigenvectors for that.
Eigenvectors are 3, but
Suppose I have a 3 into 3 matrix. 3
so
into
for
3
example,
matrix.
suppose 3 into 3 matrix. Okay, we have 3
With
eigenvectors.
distinct
Okay,
diagonal
so
elements.
okay. So let me start with this. So you are saying let this be my 3 cross 3 matrix and corresponding eigenvectors. So 1 is the only suppose eigenvalue. Okay, V
Yeah.
is equal. So a set of eigenvectors E1 is set eigenvectors E1 is what? You are saying that it will be 1 0 0 0 1 0. We know that this satisfy all the eigenvectors, right? Because anyway this is identity, so we can just take basis. But what is when I say that something is eigenvectors, that V in V I must say that E lambda, sorry, TV is equal to lambda V, right?
Yes.
In this case, if my identity is T, then I need to show IV is equal to some, since eigenvalue I know it's 1 into V. But this is true, right? I into V is 1 into V for all V in V. So this is true for any V in V. So because see what, when I said this E lambda, the entire span of this set becomes eigenspace. Because if V is eigenvector, that TV is equal to lambda V, suppose, then for any C in R, T of CV is what? C into TV, right? But this is what? C into lambda V. Now this C and lambda are numbers just from our base field. So I can just write that this thing. So now I get CV is equal to lambda CV. So now this CV form satisfies the definition of it being eigenvector. So now this implies that CV belongs to E lambda, right?
Yes.
Okay, and this is also for addition. So if U and V belongs to E lambda, then it means not that T of U is equal to lambda V, T of V is equal to, T of U is equal to lambda U, T of V is equal to lambda V. And from this, if I take T of U plus V, it is T of U plus T of V, right? But T of U is what? Lambda U, T of V is what? Lambda V. So this is lambda into U plus V. Now this U plus V satisfies the definition of it being eigenvector for lambda. So if I have
Whether U
any,
plus V is there in the eigenspace.
yes, it is eigenspace, it is vector subspace, and it is, I mean, if it is vector subspace, it is also vector space.
No,
So,
I had a for a 3 into 3 matrix, whether eigenspace will have only 3 vectors.
no, sir. Eigenspace will be entire
So
V for
what is
especially this.
the case that
If,
you have taken identity matrix?
yes.
Suppose we have distinct values in place of one.
Okay.
Some 3
Okay.
real values are distinct, and that has
Okay. Let me write
specific eigen.
this.
I mean, uh,
But still, this
for
will
this,
be okay. Then,
I will have 3 distinct eigenvectors.
yes,
1 0
which are
0
again these
0 3
eigenvectors.
0. Yeah.
Yeah. So in this
Oh,
case, eigen E1 will be now. Okay, so let me just copy this matrix. Okay, so now we have 3 eigenvalues. Lambda is equal to 1, 3, and 2. So E1 will be what? This will be 1, A0, 0, X, 1, comma 0, comma 0, right? This entire thing, E2 will be Y, 0, comma 1, comma
0.
0. Sorry, it will be 3. Y belongs to R. And E2 will be Z 0, comma 1, 0, comma 0, comma 1, such that Z belongs to R. This is
Okay.
vector subspace.
Uh-huh.
This is also, all three are vector subspaces. Okay.
Okay, understood.
Yeah.
Thank you.
Yes, sure. Any doubts in the definition of eigenspace, eigen subspace, or anything, please let me know. We'll discuss it. Is this clear that E lambda is T invariant subspace? Any doubts? Okay. Please ask. Otherwise, I will move to next question. So, now if lambda 1 and lambda 2 are distinct eigenvalues of operator, again we are working with linear, so linear operator T, then E lambda 1 intersection E lambda 2 is equal to 0. Any guesses? So this was true, okay? Any guesses for this? That if lambda 1 and lambda 2 distinct eigenvalues of linear operator T, then intersection of corresponding eigenspaces is 0. So we can just see this example. If all three are distinct, so if we pick two of them, what is in the intersection? Just an example, but in general, what this will be. Any guess that this will be true or false or anything? Okay, so let us start with any V in intersection. So if V is in E lambda 1 intersection E lambda 2, then what does that, what it means? That this implies that V belongs to E lambda 1 and V belongs to E lambda 2, right? So this implies what? T V is equal to lambda 1 V and TV is equal to lambda 2 V, right? Just the definition. So this will imply what? That lambda 1 V is equal to lambda 2 V. So this will imply that lambda 1 minus lambda 2 V is equal to 0, right? But lambda 1 is not equal to lambda 2. So this is non-zero. So lambda 1 minus lambda 2 is non-zero. So this implies what? That V is 0. Okay, so we started with any element and it's 0, so which is contained in 0. So yeah, this intersection. So this implies that E lambda 1 intersection E lambda 2 is 0. Okay, because the other inclusion is anyway trivial. 0 belongs to both since this is vector subspace, E lambda 1 and E lambda 2, 0 anyway belong to both of them and hence in their intersection. So other implication is anyway true. And we got that E lambda 1 intersection E lambda 2 is inside 0. Is it okay? So this statement is true. Okay, so no doubt. So I will move to next question. So this is now question 2. They are saying that an n cross n matrix A over R is called nilpotent if A power k is equal to 0 for some k in n, okay? And a matrix A is called idempotent if A square is equal to A. So we have to check whether following statement uh, are true or false, okay? And they are saying that A is a nilpotent matrix if and only if all the eigenvalues of A are 0. Any guesses whether this statement is true or false? Or which implication is true, the other one is false or any of that sort? Or this is true? Okay, so we'll start with since A is a nilpotent matrix, so let us try to see if A is nilpotent matrix, then this imply what? That A power k is 0 for some k belongs to n. So this imply what? 0 is the only eigenvalue of A power k. Okay, because A power k is what? 0 matrix, and we know for 0 matrix only eigenvalues are zeros. Okay, so using this we got that A power k is only 0 is the eigenvalue of A power k. Now we have to check for the eigenvalues of A. So let lambda belongs to R be an eigenvalue of A. Then what? Then say corresponding to eigenvector V. Then AV is equal to lambda V, right? And we know that then A power kV will be lambda power kV. Okay, or let me write this, or then A square V is what? A into AV, which is A into lambda V, which is lambda into AV, which is lambda into lambda V, and this is lambda square V. So we can continue such process and we get that A power kV is equal to lambda power kV. Okay. So this imply what? That lambda power k is an eigenvalue of A power k. So this implies lambda power k is 0. And once we have this, we get that lambda is 0. So when we start with any eigenvalue, lambda of matrix A, then we end up getting that lambda is 0. So therefore, all the eigenvalues of A must be 0 because this was any lambda which was eigenvalue of A, and we started from this and we got that lambda is 0. So first implication is true, that if A is a nilpotent matrix, then the only eigenvalues are 0. All the eigenvalues are 0 in fact. Now the other implication, that now suppose that now we have that zeros are the only eigenvalues of A, right? Now suppose if we need to prove that A is nilpotent matrix. So suppose A is not nilpotent matrix, or start with any matrix A which has zeros to be all the eigenvalues. So since all the eigenvalues are 0, the characteristic polynomial this determinant of A minus lambda I, this will be what? Just 0 minus lambda, 0 minus lambda, and so on up to 0 minus lambda, right? And this will be some plus or minus lambda power n based on n. Because we know that when we write characteristic polynomial, all the eigenvalues are root of that polynomial. So, and we are given that 0 are all the eigenvalues of A, then it will be of something of this form, that it will be of the form 0 minus lambda, 0 minus lambda, so on. because 0 is the only eigenvalue, and this is n times. So this will give me what? This is equal to plus or minus lambda power n. Then we know by Cayley-Hamilton theorem, so Cayley-Hamilton theorem is what? That every matrix satisfies its characteristic polynomial. So if that Cayley-Hamilton theorem is what? Every matrix satisfies its characteristic polynomial. What does this mean? That this implies for any matrix A, determinant of A minus lambda I, if this is F is equal to determinant of A f of lambda minus lambda I, then F of A is 0. When I write this 0, this is n cross n matrix 0. Any square matrix. Okay, any doubts? So this is the Cayley-Hamilton theorem. So by Cayley-Hamilton theorem, then this is characteristic polynomial. So this we get what? That plus minus a power n is 0, and since it is a 0, we can just write that a power n is 0. Therefore, A becomes nilpotent matrix. Any doubts here? That we started, or suppose let A be a matrix with all eigenvalues 0. Any doubts here? Please let me know. This is just, I'm splitting the polynomial, the characteristic polynomial, based on the fact that all the roots of characteristic polynomial are precisely eigenvalues. And we know that eigenvalues are 0. So even whatever the form of this characteristic polynomial is, it will be of this form. And it is lambda, this is plus minus lambda power n based on whether n is even or odd. And then by Cayley-Hamilton theorem, we know that this characteristics polynomial is satisfied by a power n, a. So a power n becomes 0 plus minus a power n. So this gives me a power n is 0. And that is the definition of nilpotent matrix. So that's it. Any doubts here?
No, ma'am.
Okay. Now, okay. Second, that there exists exactly one nilpotent matrix, nilpotent n cross n matrix, such that A is diagonalizable. So any guesses here? They are saying that for any n cross n matrix, if we set a set of n cross n matrix, the only there exists only one diagonalizable nilpotent matrix. So if a matrix is diagonalizable, then it must be that one of the unique. It should be one and only one. That's their guess, or that's what they are asking, that whether this is true or false. Can we produce two nilpotent n cross n matrix for any given n?
But my nilpotent matrix would be a zero matrix, right?
Yes, I mean, but nilpotent matrix are non-zero matrices. Okay, I mean, we can have non-zero matrix which is nilpotent.
Okay, so A of k would be zero.
A power A need not be 0, but A power k is 0. This is definition of nilpotent.
Yes.
But what they are saying is, I mean, A0 is also possible, but A0 non-zero is fine, but there are non-zero matrices which are nilpotent. That's what I was saying. But what I am asking is that they are talking about the uniqueness of a diagonalizability. So if there exists only one matrix which is diagonalizable, n cross n, if I take M to R, then only one set of all diagonalizable, nilpotent, then there exists only one element, say A. This is their guess, only one element. So let us start with the matrix and let's see. So first of all, we know that if A is nilpotent, then all the eigenvalues are what? 0. We just proved. Okay, this statement we proved, which was true, that if A is nilpotent matrix, then all the eigenvalues of A are what? Zeros. Then if let A belongs to M and R, Mn cross n R, A is nilpotent. Okay, suppose A is just a second. Diagonalizable. And what does that mean? That A is Q inverse DQ, where D is what? D is diagonal containing all the eigenvalues of A. But what are all the eigenvalues of A? They are 0. And Q is just some invertible matrix. But see, D is 0 matrix. So Q into D into Q inverse entire becomes a 0 matrix. So this A becomes 0. So if we start with any diagonalizable nilpotent matrix, we get that it turns out that it is 0 matrix. So, and this is the only matrix which will satisfy this. So this statement therefore becomes true. Because start with any matrix which is nilpotent and diagonalizable, and we get that it is 0 matrix. So 0 is the only possible. Any doubts?
But the statement says there is exactly one nilpotent.
Yes, so this is the only nilpotent. So for n cross n, so this is n cross n. So for n cross n, it is 1. So for 2 cross 2, for 1 cross 1, this is only this. For 2 cross 2, this is this. For 3 cross 3.
But you said there are more than one non-zero.
Nilpotent are infinitely many. But diagonalizable nilpotent matrix are unique. And that is only 0 matrix. There are many, yeah.
There, for example, in whether a 3 into 3 matrix, there is only one nilpotent or multiple nilpotent matrix. In a 3 into 3 dimension,
yeah,
can we have more than one nilpotent matrix?
Yes, we can have nilpotent, non-zero nilpotent.
But the condition will that all those matrices will have 0 eigenvalue.
Yes.
All 0 eigenvalue.
Yes. So nilpotent
all
matrix
those
means power of it should be 0. Okay. This is the
yes, ma'am.
definition of nilpotency. That A belongs to MNR, then some power must be 0. This K is some natural number. Okay.
Yeah. In addition to that, all eigenvalues of this
It's not
nilpotent
addition,
matrix
it is if and only. If it is nilpotent, then it will have 0 as eigenvalues. That's what we proved. So those are equivalent condition. You choose a matrix with all the eigenvalues 0, it will turn out that it is nilpotent matrix. And if it is nilpotent matrix, then its eigenvalues are all the zeros. That's what we proved. Okay, so if choose just, equivalent. They are just, if all the eigenvalues are zeros, then it will be nilpotent anyway. So if you choose a 3 cross 3 matrix, which is nilpotent, then we have already proved that it will have 0 as all its eigenvalue. Okay, but what we are saying that if A is a 0 matrix, then it will be diagonalizable. If it is not a 0 matrix, then it will not be diagonalizable. This is what it is saying, that if it is diagonalizable, it has to be a 0 matrix. 0 matrix is the only diagonalizable nilpotent matrix. That's what I'm saying here. Any doubts, or if what I'm saying is unclear? Or let me just
all
do this.
be
See,
said to be
this
diagonalized.
matrix, if I take this matrix, I don't know whether this is nilpotent. What is multiplication of this? This. So this is nilpotent matrix such that A square is 0. Okay. So this is nilpotent matrix.
And this
A is equal to, let A is equal to this 0, 1, 0, 0. Okay. Then A square is 0 matrix. Okay. So these imply what? A is nilpotent. And all the eigenvalues eigenvalues of A is 0, right? Because what is its characteristic polynomial? It is 0 minus lambda, 0 minus lambda minus 0, right? So which is lambda square. So eigenvalues are roots of this. So this is 0 minus lambda, 0 minus lambda. Oops. 0 and 0 with multiplicity 2. It has eigenvalues. But this matrix is not diagonalizable. Because if it was diagonalizable, then A will be some Q D Q inverse. And this D is such that it has to be of this form, right? When we say diagonalizable, the D contains all the eigenvalues in the diagonal. But if that is the case, then A becomes 0, 0, 0, 0. But A is non-zero, no? A is not 0. Oops, I must say, which is 0 as A is 0, 1, 0, 0. I hope what I'm saying is clear. I'm saying that
Yes.
nilpotent matrix could be non-zero. But if it is diagonalizable, it has to be 0. Now is it clear?
Yes, sir.
Okay. Again, you said it is okay, right?
Yes, yes.
Okay.
Okay.
Okay, so I'll move forward then. That if A is an idempotent matrix, so if A is an idempotent matrix, then both 0 and 1 are eigenvalues of A. Now any guesses? What is idempotent means? A belongs to MNR and A square is equal to A. This is the condition. And they are saying what? That 0 and 1 both must be eigenvalues of A. That is their claim. That both of them are eigenvalues. Is this true or false?
It should be true because a raised to 2v is equal to lambda square v. So there we can see that that
You
would
are
be
saying
on
that lambda square. Oh, so if I
a
write this
square
as
v
okay, A square V.
equals to lambda square v. That is what
Yes.
we'll get. And this can be only true for 0 and 1.
Okay. But does this imply that lambda has to be like it for given A, both of them will be eigenvalues? That's what they are asking. Both of them are eigenvalues. So if I give you identity matrix is such that A square is equal I square is I, right?
Yes.
So this implies I is idempotent. And what are eigenvalues? Only one is the eigenvalue. It does not have 0 as its eigenvalue. So this statement that this both is problem here. 0 will be eigenvalue, 1 will be eigenvalue, both of them could be, but not for all idempotent matrices. Similarly, we can also take 0 matrix, right? For 0 matrix, 0 square is 0. But only eigenvalues are
0.
only exactly. Only eigenvalues are zeros. So 0 and 1 are possible eigenvalues, but both of them need not be present. Possibilities are only 2, but not both of them will be present. That is what this statement is saying. Okay, any doubts here? Just both please understand and get that 0 and 1 are only possibilities, but both of them need not be present. If any doubt, please let me know. The fourth question is that idempotent matrices are always diagonalizable. And any cases for this statement? Yes.
So I can create matrix which is Q inverse DQ, where for one D would be diagonal matrix of form all eigenvalues be 0, and the other one would be, as we discussed it would be 1.
Yes.
So these are the only two cases where I can see that we can create it would be an identity matrix or a 0 matrix for which a diagonalizable is possible.
Okay. Okay. So you are saying that it need not always be true. That's what your guess is.
Mm.
I mean, see this matrix. If I take and 1, suppose. Is this diagonalizable? This is diagonal matrix itself. So everything is 0. So I can write this as identity into this matrix. Suppose if I call this A. A into identity. So this matrix is idempotent because square of this matrix will again be 1, 0, 0, 1 and so on. So A square is equal to A, right? So this implies this A is diagonalizable and idempotent. But it is not identity or what? Okay. I mean, you're getting what I'm trying to say, right?
Yeah.
Yeah. So they are saying, so this was just one of the example. So they are saying that whether it is, does this hold always? So that's what we try to, we'll see. Okay. So let us start with what this idempotent matrix does. Okay. So let start with this linear transformation of Rn to Rn. Since we are in Rn, let me write explicitly that this V going to AV. Okay, this matrix multiplication and all the eigenvalues of this LA and this A are similar and so on. We know that, we have seen this. So suppose that rank of LA is R. Okay, this is linear transformation, so it will have some rank. Okay, so then there exist R linearly independent vectors. Okay, such that U1 to UR, or let me write this range of this LA is span of this U1 to UR. Okay, and this U1 to UR are linearly independent. Then by definition, what this may imply that this UI is AVI for some VI, right? Because, or let me write, since UI belongs to range of LA, this implies that UI is equal to AVI for some VI in R n. So if I take this AUI now, it is what? A square VI, which is what? AVI. But what is AVI? It is UI, right? So I get what? That AUI is UI. So if I write this properly, this is one UI, right? And this is true for all this U1 to UR, which were spanning the range. Is this clear so far? I just obtained that. Let me write this here. UI is in range, so UI is AVI for some VI in Rn. Then we get that AUI. I'm just calculating this. AUI is again applying A on both of this. So AUI will be A square VI. Or I mean, this is clear, right? If anybody has doubt here, please let me know. Otherwise, I will move forward. So these imply what? That one is eigenvalue of A with eigenvectors UI. Okay, so now then by rank nullity theorem, or our dimension theorem, I mean, nullity will be what? Dimension of Rn minus this rank of LA, which is n minus R. So if that is the case, then this implies that there exist in linearly independent vectors say W1 to Wn minus R such that null space of LA is actually span of this W1 to WR, right? So I'm just writing basis of this. And what does this mean? A of Wi is 0i, right? A of Wi is 0. And if I am to write this properly, this is 0 into Wi. Is this okay? So this implies what? And this is true for all I between 1 and n minus r. So this will imply that 0 is eigenvalue with Wi's as eigenvectors. Okay. So this implies that E of 1 is this U1 to UR. And if I'm writing here E0, I mean eigenspace of 0 is this W1 to Wn minus R. Is this okay so far? Any doubts here? From the range space, we got these elements here. And from nullity, we got these elements here. And this A was idempotent operator or idempotent matrix. This is matrix multiplication by a idempotent matrix. I did not write here. Let A be an idempotent matrix. And then we have got all this. Okay, and apart from this, we have this theorem which we proved. I wanted to prove the diagonalizability. Okay, I already have these R elements and these n minus R elements. So if I can say that union of these two, this E1 and E0 forms a basis of Rn, then I can declare that this matrix A is idempotent diagonalizable matrix, because we know that a matrix is diagonalizable if all its vectors, eigenvectors, not all, I mean linearly independent eigenvectors form basis. Okay, so we have then this theorem which talks about the linear independence of eigenspaces or eigenvectors corresponding to different distinct eigenvalues operator on V, and lambda 1 to lambda k are, this is proved in the lecture by the way, be distinct eigenvalues of T. Suppose Sj be, oh, E0 will be span of this. Be a linearly independent set of eigenvectors with eigenvalues lambda j. Okay, then what they are saying is that then S is equal to S1 union S2 union up to Sk is linearly independent. Okay, this is the statement. So I can very well take this S0 to be this U1 to UR and S1 to be W1 to Wn minus R. Then by above theorem, S is equal to this U1 to UR, W1 to Wn minus R. This forms a linearly independent set. And since dimension of Rn is n and cardinality of S is equal to n with S linearly independent, or let me write this here, with S linearly independent, implies that S is basis, and S is basis containing all the eigenvalues, right? Because these ui's and wi's are eigenvalues corresponding to 1 and 0s. Eigenvectors. This implies that this LA, which is equal to say that A is diagonalizable. Okay, any doubts here? We
But
started with the, yes.
would we get an eigenvectors in that new space we have created? The S set S.
Yes, sir.
Do we have would we have n different eigenvectors here?
Yes.
And how do we prove that?
These are eigenvectors, na? We started with the eigenvectors.
No, but we need n eigenvectors, right?
So these
So
are R
for it
and
to
n
form
minus
a,
R. So n
for it,
R plus n minus R
okay,
is n.
yeah, sure, okay.
Okay, so these are n elements together. Is it okay now? Just a second. Sir, is this okay?
Yeah, this is okay, but
Yeah.
the only confusion is how do we conclude how do we approach this problem where we want to see that first we want to consider the rank and then again for another eigenvalue we want to consider the rank nullity theorem.
Yeah, I mean, that is something kind of tricky. I mean, this is theorem. I mean, this is not something we can just try and obtain. I mean, yeah, this is something which one should know beforehand. I mean, nobody can just start doing something and obtain this. Yeah, I mean, the intuition that how to start with something like this is difficult. That's what you are saying, right?
Yeah, I may note the individual theorems, but to use those two theorems in this particular problem.
Yeah. I mean, we wanted to anyway show that this is diagonalizable, right? So we somehow wanted to, one intuition could be we somehow wanted to obtain eigen vectors, and we know 0 and 1 are the only possibilities. So even if we had started with the zeros, I mean 0 and 1, so the null space, if 0 is the eigenvalue, then corresponding eigenvector is basis of a null space, set of eigenvectors. Okay, so we can start with this at least, and then the rest will be something belonging to range, and for range we can obtain this. I mean, starting from here and then going to nullity is a bit difficult compared to starting from nullity and then going to, I guess, range. That is more obvious than what I did, I guess.
Okay.
I don't know the intuition for now, but yeah, this is, I mean, what I did is understandable, right? Or is there any query like how this step is coming or something like that?
Oh, that is fine.
Okay. So shall I move ahead now? Is it okay?
No, in this theorem,
Yes, sir.
S0 is actually the column space, S1 is the null space, right? S0 spans the column space.
Yes, sir.
And S1 space, and we are combining this and we are telling that it is diagonalizable.
Yes, but what we also got is that LA is from V to V. Okay.
Okay.
So this something which we started from the range is also giving us an eigenvector. So now when I'm writing this UI is in domain. Let me write here. The same UI which I started from element in codomain, using this property that this A square is this, I obtained that this UI, the same UI.
Okay. That
In
means
the
here domain and
domain
range is
acts
same.
as an eigenvector. Sorry, sir?
No, here that means our domain and range both are same. Is it right? We are mapping from the same space.
No, domain and range are not same. Domain and range can't be same. Domain here is V and range is some span of these R elements. Dimension span of this U1 to UR. Okay, so image is equal to, I mean, range is not equal to V. That is for sure. Because this is spanned by R element and this has dimension N. So they are anyway not equal. This is inside domain. This is inside domain. This is not entire domain, inside domain. So it is like I had V here, I had V, and both are same elements. So something I'm taking from range. And when I trace them back, I see that these elements are acting as these dots are acting as eigenvectors of V. That's what I'm doing here. So I'm starting from here and I'm going here to see that they're same element. I mean, we can do this because we have this liberty that both of them are same, that domain and codomain are same.
Yeah, in this actually, first we are considering that even though our dimension is n dimension, only R independent vectors are there.
Yes, yes.
Then that means remaining all are null space. Means it.
Yes. This is from the dimension theorem or rank nullity theorem. Yes.
And for independently, we are getting a independent eigenvectors, and we are taking a union of that, and we are saying that it is spanning the.
Yes. So we are not proving that it spans, but what we are doing is we are using this theorem, which says that union will be linearly independent set. So now we were talking about the basis of Rn. And now I have a set containing n elements which are linearly independent. So I can declare that this set is basis. And once I have that the basis containing eigenvectors, I can say that A is diagonalizable.
Now, whether this implies that A is always, means any matrix is always diagonalizable, is whether or only that idempotent matrix only is diagonalizable.
Idempotent matrix only, right? Because we are having this 1 and 0 here.
Okay.
We know that 1 and 0 are the only eigenvalues. Otherwise, we can't say.
Okay. Okay.
And we also use this, na? This equality is quite important here. Let me highlight this. We use this. This is not true for any matrix. This is only true for idempotent matrix. For if I start, so as you were saying that I can start with any matrix and arrive at this, it's not possible because this step is not there for any given matrix. Is it okay?
Okay.
Yeah. So I will move to now the next.
So that statement is true, right?
Yes, this statement is true. Yes, this is true. Let me write it here that this is true. Now this question 3, now check whether following matrices are diagonalizable matrices over R or not. Okay, so first is this. And what is guess? It itself is a diagonal matrix. So I can write if this is A, then A is equal to identity into, or let me write diagonal pi E into I, but this is anyway AI. So let me write this. This implies A is diagonalizable. This is true. It is diagonalizable. And next is, these are easy questions. Okay, we just have to check whether the matrix is diagonalizable or not, and all of them are too close to matrices. So what is eigenvalues of this matrix? So since this is upper triangular, diagonal forms the set of eigenvalues. So lambda are 1, 1. So multiplicity of 1 is 2. Multiplicity of lambda is equal to 1 is 2. Oh, now we also know one fact that, or we proved a theorem that A is diagonalizable if and only if dimension of E lambda is equal to multiplicity of that lambda. Okay, so we will try to see whether we can, since the multiplicity is 2, we have to check whether dimension of E lambda is 2 or not. Okay, so what this means that AV is lambda V, and we know lambda is 1. So 1, 2, 0, 1 is equal to x, y, let V be x, y. Then it is 1 x, y. So this implies what? X plus 2y is equal to x and y is equal to y. And from this what I get? That y is 0, right? So this, therefore E1 is contained in this x comma 0 such that x is in R. And dimension of this is 1 for this. And E1 is non-zero. So dimension of E1 then has to be 1. Otherwise, if it was 0, then dimension of 0 would be, or let me write this, dimension of E1 is less than equal to 1 because it is contained. We know this. And it's non-zero, this implies dimension of 1. E1 is 1. Any doubt here what I did? How I arrived at this here? Any doubts?
No, this is only we say it as a geometric multiplicity. Is it?
Yes. This is geometric multiplicity actually. This is algebraic multiplicity, and we just got that this dimension of E1 is called as geometric multiplicity. But we so far did not use that term in our lectures. So
Okay.
but this is geometric multiplicity, yes.
That
So
multiplicity, can you explain?
Let me write here 1 or lambda 1 lambda. Yeah. Yes, sir. You were saying something.
How you arrived at whether it is number of eigenvectors?
Yes. So this you
Eigenvalue.
are asking?
Yes.
Yes. So this is number of eigenvalues. So it is like how many times that eigenvalue is occurring. So for example, in this matrix, 3, 2, 3, multiplicity of 3 is 2 and multiplicity of 2 is 1. So eigenvalues are 3, 3, 3, 2, 3. So how many times 3 is occurring is multiplicity of that eigenvalue. So if lambda is eigenvalue, then how many times that lambda is repeating? That is the multiplicity. For example, in identity matrix, n cross n identity matrix, 1 repeats n time. Okay, 1, 1, 1, 1, 1, 1, n times are eigenvalue. So multiplicity of 1 becomes n. Similarly, in 0 matrix, multiplicity of 0, since 0 is the only eigenvalue, multiplicity of 0 becomes n. Similarly, for any nilpotent matrix, the same thing would happen. Okay? It is just counting how many times that eigenvalue is occurring in the characteristic polynomial.
In this example, what you have written, so here
Mm-hmm.
first we have to find the eigenspace for 2. If
Mm-hmm.
that dimension is also 2, then we say it is diagonalizable. Is it like that?
Yes.
We have to
So
independently find.
Yeah, so if I want to check whether this matrix is diagonalizable, what I need to do is find E3 and E2. And if dimension of E3 is equal to this multiplicity of 3 is 2, and if dimension of E2 is 1, then this matrix A is diagonalizable.
Okay.
Okay? Yeah. This is anyway a diagonal matrix itself, but in general, when we have non-diagonal or some not good looking matrix, then in that case, this is how we need to go ahead with finding diagonalizability of a matrix. Since this was easy 2 cross 2 matrix, so yes. But I hope now it is clear what is multiplicity of eigenvalue. Now the third one. Yes, this one. Let A be 1, 1, 1, 1. And now, any guesses what will be eigenvalue? The determinant of A minus lambda I is 1 minus lambda square minus 1. So this will be lambda square minus 2 lambda plus 1 minus 1. So this is eigenvalues are 0 and 2. Both. So 0 has multiplicity 1, 2 has multiplicity 1. Okay. And now since we have this, by this theorem, which we know that if there are k distinct eigenvectors, eigenvalues, then there are k distinct eigenvectors. We wrote in the very beginning of the class. Yeah, if T is a linear operator on finite dimensional vector space V, and if there are k distinct eigenvalues, then we have k distinct eigenvectors, and they form a linearly independent set. Okay, so using that, we can say that since there are two distinct eigenvalues, this implies if corresponding eigenvectors are, let's say v1 comma v2, then or v0 comma v2 form basis for R2. Okay, because when I write this, I consider it as LA from R2 to R2, going V going to AV. Is it okay? Or if this is confusing, just forget this. So if there are n distinct eigenvalues, if matrix is n cross n, if there are n distinct eigenvalues, we already proved in the beginning of the class that they form basis for the corresponding vector space. So that gives us that this A is diagonalizable. Therefore, A is diagonalizable. Let me write. If doubts, please let me know. And now this 1, 3, 3, 1. Then determinant of A minus lambda I is lambda minus 1 minus lambda, 1 minus lambda, minus 3. So it is this lambda square minus 2 lambda plus 1 minus 9, which is lambda square minus 2 lambda minus 8. And we can get that this is determinant of A minus lambda I is equal to, this will be minus 4 plus 2, I guess. Yes. So again, distinct eigenvalues, two distinct, or let me write, two distinct eigenvalues, therefore diagonalizable. When I'm writing this 2, I mean this is, since M, this A is in 2 cross 2 matrix, therefore when I'm having two distinct eigenvalues, therefore I'm declaring that it is diagonalizable. If A was some n cross n matrix, then I must get that if n distinct eigenvalues, this implies that A is diagonalizable. In fact, we also proved this in the first the first question of true false second part, that if there are n distinct eigenvalues, then it becomes diagonalizable matrix. Okay, if there are no further doubts, this is the last. Yes, sir.
Our third question, no?
Yeah,
one of the
third.
eigenvalue was 0.
Yes,
so
sir.
normally if one eigenvalue comes 0, A is not an invertible matrix. No, its determinant
Yes, sir.
is 0. Even that case also, it is diagonalizable.
Yes, sir, definitely, because zero matrix itself is diagonalizable, right?
Okay.
Yeah. Invertibility has nothing to do with diagonalizability.
Okay.
Yeah. In fact, idempotent matrix, this idempotent matrix which we saw in the beginning, this is also not invertible because determinant of this matrix is also 0. But we proved that any given idempotent matrix is diagonalizable. In fact, determinant of any given idempotent matrix will be 0 because 0 is one of the eigenvalues. So it will never be invertible matrix, except, not never, but except for identity and so on. But if the determinant is 0 of a idempotent matrix, then it is not invertible, but it is always diagonalizable.
Okay. So we have to see only we have distinct eigenvalues. So that is enough for the
if distinct eigenvalues, then if there are no distinct eigenvalues, then this case we were talking about the multiplicities.
Yeah. Okay.
In that case, we have to check these multiplicities. If eigenvalues repeat, then we have to check whether dimension of E lambda is equal to the multiplicity of that lambda. If that is the case, then we can say diagonalizability. So there are multiple cases based on how the lambda is occurring.
Okay, clear.
If all distinct, then we can just declare that it is diagonalizable. If not distinct, then this is the second case which we can use to declare that it is diagonalizable. Because, for example, identity matrix has only one as eigenvalue. I'm repeating this again, but it is diagonalizable. Okay, so repeating is not a problem, but not repeating is good thing.
Okay.
Oh, okay. So, okay, no doubts, right? So I can move ahead, right?
Yeah, it is clear.
Yeah, sure. So now for this, the determinant of A minus lambda I, so let me write this A, is this is just minus lambda plus 1. So this is lambda square plus 1. But this does not have any root. Does not have any root in R. Okay, and we were talking about diagonalizability over R. So therefore, A is not diagonalizable. Because no eigenvalues, no diagonalizability. Because there is nothing to check AV is equal to something V, but that something doesn't exist, so it's not diagonalizable. Okay?
No, that means if imaginary roots comes, it is not diagonalizable.
Yes, in R, over R. So the question talks about over R. Here it is over R. If the question was, because vector space can be very well be on complex. So if my vector space is complex vector space, then and I'm talking about diagonalizability over complex set or set of complex numbers, then it will be diagonalizable. But over R it is not, because if I'm talking about diagonalizability over R, then I expect eigenvalue to be from that field R. If I'm talking about complex, then I will expect the eigenvalue to be a complex number. Or real number is not a problem, because anyway real number sits inside complex. So complex matrix can very well have real eigenvalue and so on.
Okay.
Yeah. So moving to next question now. Just a second, let me see. Let us start with this question. Let A be an n cross n matrix that is similar to an upper triangular matrix that has distinct eigenvalues lambda 1 to lambda k with corresponding multiplicities. So corresponding multiplicities means how many times that lambda I occurs when we write down all the eigenvalues. Say m1 to mk, okay? So what does this imply? That lambda 1 occurs m1 times, lambda 2 occurs m2 times, lambda k occurs mk times, okay? Then they are asking to check whether following statements are true or not. Okay, so let us start with the first one. That what they are saying, that the trace of this matrix A is summation mi lambda I from 1 to k. This is first question. Any guesses whether this is true or not?
True, madam.
Yes, it is true. So we have guessed that it is true, but this is true for any matrix A which is similar to an upper triangular matrix U. Okay. And U is upper triangular matrix of containing these eigen values, so on. So where Q is invertible and U would be of any sort. I mean, I can have this lambda 1, lambda 2, lambda 1, lambda 2, and so on. But when we count this lambda 1s, they will occur only m1 times. So without loss of generality, I can just assume this. I mean, it won't create any problem that they are clubbed, that lambda 1 are like this, lambda 2 are like this, then so on. lambda and start and ends like this. Okay, U is of this form. For upper triangular matrix, we know the diagonals give the eigenvalues. So if I'm saying that it is upper triangular matrix with, so this, let me write here, this m1 times, this here m2 times, and this here mn times. Okay, so what is trace? It is just addition of this thing. So trace of U is summation I from 1 to k mi lambda I, right? That is not a problem. But now I have to conclude that this trace of A is this thing. They are asking about trace of A. But what we have is this thing, Q inverse UQ. Okay, we know trace of this thing. What can we do? We have to talk about trace of A and not trace of U. The statement is true, that is correct. But now we need to prove this. Okay, we use this long back, I guess, in our lectures, that trace of AB is equal to trace of BA. If not, then even if we are using this for first time, we have this thing. Okay, trace of AB is equal to trace of BA. So this thing is same, right? Q inverse U, if I club them like this, then this will be this, Q inverse U. And now this trace of QQ inverse will be now, let me just write everything. Trace of identity into U, which is trace of U. And we already know that this is summation I from 1 to k mi lambda I. Is it okay now? Any doubt? We just use this property. Trace of AB is equal to trace of BA. And now we got the trace of A. So we started from an upper triangular matrix and we got the trace of A when it was similar to that upper triangular matrix. And this same applies for diagonal matrix. So if A is equal to Q inverse diagonal Q, then again the trace will be same. Okay. So in upper triangular case, this matrix here is, some entries will be here. I'm writing star. So now second question they are asking is that second.
Ma'am, A is diagonalizable, ma'am.
Sorry, sir?
A is diagonalizable. Last.
No, A need not be diagonalizable.
Why, ma'am?
This is upper triangular matrix, not diagonal matrix. And upper
Diagonalizable.
triangular matrices need not be diagonalizable.
Okay.
Yeah. Okay, upper triangular matrices need not be diagonalizable. I mean, did we saw an example of upper triangular matrix which was not diagonalizable? Let me see.
Suppose
Yeah,
eigenvalues are distinct.
Yes, sir.
Upper triangle matrix diagonalizable.
If distinct, definitely, yes.
Always upper triangle matrix not diagonalizable.
Always it need not be. For
Yes.
example, this is upper triangular.
Yes, diagonalizable.
But it is not diagonalizable. We just saw, right? This dimension was less than, let me write it there, less than multiplicity is equal to 2. So this was not diagonalizable.
Here eigenvalues are same, ma'am.
Yes, sir.
Suppose
But yeah,
eigenvalues
if
are
distinct, then by default we got that it will always be diagonalizable. If
yes,
it need
yes.
not be upper triangular, lower triangular, whatever it is, if it has diagonal distinct
Yes, ma'am.
eigenvalues, it will always be. Yes.
Okay, okay, I understand.
Yeah. Now trace of A is, they are asking whether it is this. And lambda I m power I is trace this of A. So A is matrix which is similar to an upper triangular matrix. So this is not true because we already proved that trace is this mi lambda I, and what they have given here is something different. So let us just work with this upper triangular matrix. So this is upper triangular, okay? This is diagonal matrix, so it is also upper triangular matrix. So trace of A is what? It is 3 plus 3, which is 6. But if I go with this formula, if this summation lambda I mi, so lambda is only 1 to 1, so only 3. And multiplicity mi is in the power, so 3 square, which is 9. So this is not true. Okay, so this was nothing to think about. So now next, then determinant of A is summation I from 1 to k lambda I power mi. Is this true? Let's see.
True, ma'am.
It is summation of lambda I power mi. Determinant is summation.
It's true, ma'am.
Okay, it's actually it's not true. Determinant is product of all of them. Here it is summation. So that's why it's not true. Let us see this example. So if I take this matrix 3, 3, 2. Okay, so it's determinant of this matrix. So when I write this, I mean this. This is upper triangular matrix. Its determinant is 18, right? 3 3s are 9 and 2, 18. But if I write this summation I from 1 to 2, now there are two distinct eigenvalues. Okay, and lambda 1 power mi. So if my lambda 1 is 3, 3 power mi means 2 plus lambda I 2 power 1. So which is what? 9 plus 2, which is 11. So these means that determinant of A is not equal to summation I from 1 to k lambda I power mi. Is it okay?
Okay, ma'am. Clear, ma'am.
Yeah. Now what you are saying is, now I will write it here. It is product of all of them. It is determinant of A is product I from 1 to k lambda I power m. Okay, now
This is correct, ma'am. Okay.
yeah, this one is correct. This one is false. This one is not true. And now this one is correct. Product of all of them. This is true. And let us prove let us prove this. So A is what? It is Q inverse UQ, where Q is invertible. And U is some, and U is upper triangular. Say, let U be this. Again, I'm writing this. Lambda 1 to lambda k. Sorry, lambda 1. M1 times, lambda 2 to lambda 2, M2 times. And this is lambda n to lambda n. nk times. So this could be non-zero entries here, but everything below diagonal is 0 since this is upper triangular matrix. This occurs m1 times, this occurs m2 times, and this occurs mn times. So we know in upper triangular, determinant is product of diagonal entries. So which is lambda 1 into lambda 1, lambda 1 dot lambda 1 up to lambda 1. This is m1 times lambda 2 to lambda 2, m2 times dot dot dot. Lambda n to lambda n. This is mn times. So we got that this determinant of u is product of I from. So if I am to write this L in compact form like this, then it is product of I from 1 to k lambda I power mi. It's okay, right? But now again I need to prove that for determinant of A. Determinant of A is what? Determinant of Q inverse U, whatever it is. But we know that determinant is multiplicative. That is determinant of, we also proved this in our previous lecture, that determinant is multiplicative. Okay, and determinant, so this cancels. These are just numbers, so it get cancelled, and this is equal to determinant of U, and which is what we obtained is lambda I power mi. It is okay? Is it okay? Any doubts here?
It is clear.
Yeah, it is clear. And now this, which we just discussed, but let us again discuss not same thing, but it properly. Diagonalizable over R. And what is the guess? A is some Q, U, Q inverse, or A. We can start with an upper triangular matrix itself so that we can. So A can always be written as identity inverse or I, U, I inverse, or anything which you, any form which you like. Can we always say that A is diagonalizable? A is matrix which is upper triangular. With eigenvalues, we know whatever is there in the diagonal with corresponding multiplicities. Lambda 1 to lambda k, and oops, here it must be lambda k. I made a mistake here. I think here also I wrote the same thing. Otherwise, it's fine. Yeah, I was talking about this. An upper triangle. They are saying that A is upper triangular, similar to an upper triangular matrix. A itself need not be upper triangular matrix, but it is similar to an upper triangular matrix, and they are saying that whether that A is diagonalizable over R or not. A is similar to an upper triangular matrix, so A itself could be an upper triangular matrix. That is the hint.
So if eigenvalues are not in R, then it would not be.
But
As we saw
A
in
is
the
A is matrix in MNR. Okay, so and U is also in MNR. A, U, Q, Q inverse, everything is in MNR. So entries are anyway real. That's not a problem. The diagonal which we are talking about here of U. So U, if it is of this form, let me write lambda 1 to lambda 1, lambda 2 to lambda 2, lambda k to lambda k. All of them are, I mean, real eigenvalues, real numbers. Lambdas are not problem here, like, because we are in A and this Q inverse everything is in M and R. And also one thing is that for upper triangular matrix, since matrix itself is in R, all the eigenvalues will be in R. So eigenvalues will always exist in upper triangular case. Problem is with eigenvectors, whether they exist or not. Because if it is upper triangular matrix, forget about this matrix. If U is any upper triangular matrix of this form, lambda 1 to lambda n, then diagonal, so then determinant of A minus ui is what? A minus lambda u minus lambda I is lambda 1 minus lambda, lambda 2 minus lambda, so on up to lambda n minus lambda, right? So this will give me what? That lambdas are lambda 1 and so on up to lambda n. And this matrix is in MNR. So eigenvalues will always exist in case of upper triangular matrices. Is it okay?
Yeah.
But we are talking about its diagonalizability. Existence of eigenvalue doesn't imply diagonalizability. So in our case, luckily we have eigenvalues, but whether it is diagonalizable, we just saw one thing just before discussing this. Invertibility and everything which we were talking about. So this matrix which we just saw earlier, which I showed, this is not diagonalizable because we saw that earlier from earlier example. A is equal to this is not diagonalizable. A is similar to an upper triangular matrix because I can just write this. A itself and I. It is similar to an upper triangular matrix, but A is not diagonal. Anyway, I have written because lambda is only 1 with multiplicity 2, but dimension of E lambda, which we saw, E1 was 1, which was strictly less than multiplicity of 1, which is 2. Okay, so this is not diagonalizable. So upper triangular matrices need not be diagonalizable, and any matrix similar to an upper triangular matrix, such upper triangular matrix need not be diagonalizable. Is it okay?
Now here the question is whether matrix A must be diagonalizable if A equal to Q is it?
Yes, yes.
So that is not true always.
Yeah, not true always, because this example, this Q here is acting, I is acting as Q, and A itself is acting as U.
This A is upper triangular matrix, whether it is
Yes,
given.
it is upper triangular matrix. A is upper triangular matrix.
That is a given. That is given. The question
That
itself,
is,
or we
no,
assume.
it's not given in the question. We are giving counter example. We have to say that this statement is false.
Okay. Okay.
Okay, so we are giving this counter example. So this is counter example. Counter example to above statement, therefore not true. Therefore, statement is not true.
If A is diagonalizable,
No,
then
A is not diagonal. This A is not diagonalizable.
suppose if A is diagonalizable, then A is similar to upper triangular matrix is possible.
Yes, because A is diagonalizable. Then A is what? Q inverse DQ, right? D is diagonal where? But diagonal matrix is always upper triangular matrix, right? It is considered as upper triangular matrix.
But converse not true.
Converse is not true.
Yeah, yes.
Converse means when I talk about the statement as upper triangular matrix. If A is similar to diagonal matrix, then it is diagonalizable. But if A is similar to upper triangular matrix, then it not be diagonalizable. Is it okay what I said? If it is similar to diagonal matrix, then by definition itself it becomes diagonalizable. But upper triangular case, we just saw that if it is upper triangular matrix, if it is similar to upper triangular matrix, it need not be. Any doubts here?
Okay, ma'am, clear.
Yeah. Yeah, let us do work with this. Just this one is question. I guess it was 6 or 5. I guess 6. Let T be a linear operator. This is clear, right? Please let me know if there are any doubts. Okay, you can think meanwhile and let me know if there are doubts in previous question. On a finite dimensional vector space V, suppose lambda is an eigenvalue of T with eigenspace E lambda. Then check the following whether true or false. First statement is that the 0 and the 0 subspace and V are always T invariant subspaces of V of T. They are saying that 0 subspace means this, and V are always T invariant. So what is T invariant? I just wrote statement definition earlier, but let me write again that if T is from V to V, W subspace of V is T invariant if T of W is contained in W. Okay, so this is the definition. This is shorthand. So what we need to check that T of 0 is again in 0 or not. So but what is T of 0? It is 0, which is anyway contained in 0, only element. So therefore, T invariant, let me write here 0. And now for V, let V in V, then what is T of V? Whatever whatever it is, it will land in V, right? Even if it is some W, it will be in V. So therefore T invariant. Or is it not? It is. I mean, let me know if there are any doubts. I mean, these are trivial, but sometimes it becomes difficult to get what is happening. So please let me know if this is not clear.
This TV to equal to W, how we are saying? Is it because
It will
TV
be
to
something. It will be something. It will be something. This W is and this W which I wrote were not same. Let me write you. It could be anything, but it is some element in V, right? T is from V to V. So this element in V. This is some element in V.
this
This clear,
linear
right?
operator?
Yeah, T is linear operator from V to V. So image of any V is inside V. So this imply what? That this range or this V, TV is contained in V. This is anyway the default statement. When I write TV, TV is all TV such that V belongs to V. This is anyway contained in V because this is the definition. And we are starting with both of them in same subspaces. I mean, domain and codomain has to be same when we talk about this. Otherwise, it doesn't make sense because this TW is inside codomain. And this W here, it is a subset inside domain. Okay.
I have one basic doubt. That is
Yes,
this
sir.
linear operator and linear transformation. So linear
Sir,
operator, domain and is it that's we call
yes,
it?
sir. Yes, sir. Yes, sir.
Where a transformation means the
It
domain
could be
and
from any vector space to any vector space. It could be same or different. But when we
So-
say operator, it is from same
that means
vector space to same.
linear operator is also, we can call it as a linear transformation.
Yeah, definitely, no problem. But
Okay.
it is just to specify. I can very well write T is a linear transformation from V to V. No problem. Yeah.
Okay. Okay.
Yeah. Now, is there any doubt? Yes, sir.
Linear operator from V to W is not possible.
The definition, I mean, we call it operator when it is from V to V. So if it is different, then we call it transformation. It is just to specify. For example, every upper triangular matrix is every diagonal matrix is upper triangular, but there is some difference. So consider linear operators as a diagonal matrices and the linear transformation as upper triangular matrices. So transformations.
But Gray's book said that linear operator is V and W are same field over the vector space, then T is linear operator. Okay.
Yeah. Yes.
Erwin Gray's book.
Sir, could you please read out again?
T is defined from V to W is linear operator. V and W are vector space over the same field. Then,
okay. So yeah, I mean, that is not a problem. I guess linear operator, linear transformation are sometimes used equivalently. That's not a problem. I mean, it depends on definition to definition how somebody wants to call it, but they are just names. The basic statement to both of them is it is linear transformation satisfying linear condition from one vector space to other vector space. Okay, if there are two vector spaces mentioned when we talk about T, so we can assume that it is from some V to W. If it is just said that T is linear transformation on V or T is a linear operator on V. So only thing we are talking about is V. So in that case, it will be a linear transformation from V to V. So it is just the naming. Please look into like what they are talking about. I mean, in whatever lectures we have considered, so in the lectures we are following linear operator for same vector space to same vector space, but there are different texts which can be considering different definition for that name as sir suggested. Okay, any doubts now?
Okay.
Yeah, so just quick question.
At the same regard, say if that V and W, if both are at same dimension, then also we can call it as linear operator. Suppose that whatever told now V and W, if both are the same, suppose R2 to R2 or R3 to R3.
Yes, I mean when it is finite dimensional, then yes, it is equivalent to saying that they are from same vector space because we saw they are isomorphic and so on. Right? I mean that's what you were asking, right?
Yeah, means yeah, the same thing.
Yes. So this quick that nullity, I mean nullity of T, the null space of T is a T invariant subspace. Subspace of V. And let us check. What is null space of T? Let me write it again. All those V in V such that T of V is 0. Okay, so if I take any V in null T, then T of V is 0. which is anyway element of nullity, which we know. So therefore this null space is T invariant. Any doubts here?
No, ma'am, clear.
Yeah. And this E lambda is T cube invariant. I know we are over time, but let us finish this and then we can stop. So E lambda is what? As we all know, it is V such that TV is equal to lambda V. And so we are asked that it is T3 invariant. So when I say T3 invariant, it means that W is T3 invariant. Then similar to then T cube of W is inside W. This is the definition. T cube means what? T applied 3 times on W. Or let us start. We will see what it is. So let V be. So we are talking about invariably or invariantness of E lambda. So let V belongs to E lambda. Okay. Then what is T cube W? T cube V. When I write this, I mean this is T cube applied to W for all W in W. Yeah. And this is what?
T
T
square of
square.
T of V.
Yes, exactly. Which is T square of lambda V, because V is in E lambda. This implies TV is equal to lambda V. And this is lambda T square V, and which is again T of T lambda, sorry, TV, which is, I'm just directly taking lambdas outside, and it is now T cube V. And anyway, yeah, T cube V. So these imply what? Now this V I started with, and T cube is this element. So what I got that T belongs to E lambda, then T cube V is lambda cube V. Now I want to check whether this element, whether this belongs to, this is my question, that whether this belongs to E lambda or not. So when do I say that something belongs to E lambda, that is eigenspace? It means that T of this element has to be lambda times this element, right? I need to check this, whether this holds or not.
A scalar
Right.
multiplication.
Yes. Yes, definitely. Scalar multiplication. What we have is lambda cube TV, and which is what I get right now is lambda cube lambda b, but that is nothing but lambda into lambda cube b. And yes, this is what we needed. So therefore, and now I can conclude that therefore this E lambda is T cube invariant. Is it okay? Just because
Can
we
you
arrived here is not enough to conclude this. We have to check whether this obtained element is in our W which we started. Yes, sir.
can you just tell how that check condition, how you arrived to that?
So see, what my question is that V belongs to E lambda. I need to check that whether T cube lambda belongs to E lambda or not. This is my condition, right? For
Yeah,
T
correct.
cube invariance. This is what I need to check. Then whether this happens or not. So I started with V. Then what is T cube V? This thing. So this is just this element. What we got it? It is lambda cube V. But I need to check whether this belongs here or not. So I checked it using this condition, because this is the definition, right? When do I say that something belongs to eigenspace? That it has to some eigenspace corresponding to lambda. It has to satisfy this condition. So for this to belong to E lambda, T of this element must be inside E lambda. This is my condition, this. And what is E lambda means that T of lambda cube, T cube lambda must be, like, is lambda times T cube lambda, which is lambda times lambda cube lambda. Sorry, V. Oh my God. I hope this is clear. T cube V. Is it okay?
Okay. In general, this operator invariant means if I take any vector from that space, if I do that operation, it will be in the same space. Is it?
Yes, that is, yes. When I operate, so it is like whether image is again inside that set or not. So it is like if I have this two vector spaces and this is my W, and again, so this V is same V and this is again W. Okay. So when I take image, the image could be inside the same thing or it could land outside also. So when the entire image of this set lies inside this W under this T, then this W is called T invariant. This is what it is about.
Okay.
Whether
Okay.
the image again is contained in the same set or not.
So in short, we're saying it is bijective.
No, we are not saying that. So for example, let me show you this. T is from XY. So T is from R2 to R2. Or suppose my T is this. Oops, not this, this. Okay. Then this subspace, let me call this subspace W is my this. X comma 0. So that X belongs to R. Okay. Then T of W is what? Again, it is X comma 0, right? Which is, I mean, for X comma 0 belongs to W. T of X comma 0 is again X comma 0, but which is anyway in W. So therefore, this W is T invariant, right? Under this T. But T is not bijective. And in fact, since we saw that we, or let me give this for 3 x, y, z. So it will be clear x comma y comma z. X comma y comma 0. Or let's just take this. I can take W to be this. X comma y comma 0. And we know x, y in R. So this is subspace. Now I have to check whether this is T invariant or not. Then I need to check this T of W. T of W is, it will always be of this form. Right? So it is contained in W, but not bijective, even for W. Even on W, it is not bijective. I mean, I hope what I'm trying to say here is clear. I'm saying that even on W, it is not bijective. So we can't talk about the entire bijectiveness. It is just that whether this T of W is inside W or not.
Okay.
Okay, it is not saying that T of W is equal to W. So no bijectivity.
In that case also W is T invariant also. Now whatever.
Yes, definitely. T invariant. Yes, it is inside W. So T invariant.
Okay. So it need not be that that XY should be there. Even X0,
Yes, yes.
0, Y0, 0, both are in W. So it is always T invariant.
Yes, yes, yes. And see here also, because, yeah, this V when we were talking about, 0 subspace V is always T invariant. So even, so this T is not given whether it is surjective or not. So if T was not surjective, then this image or T of V, this set, will be proper subset of V if T is not surjective. I mean, I don't know whether I'm making this too complicated for you, but I wanted to mention this. that if I take entire space, which is we know is T invariant, but if T is not surjective map, then this is not bijection. In fact, not surjection. I'm just making things more clear and
Yeah, it is clear.
yeah. Any doubts now for this? I mean, how things are happening, whether this is bijective, surjective. No surjectivity or bijectivity is talked about here. We are just checking whether image is landing inside the set or not. Okay, or in fact, this null space, if we see null space, we just proved that it is T invariant, but T of null space is in fact just 0. So if it is not injective map, null space will be something non-zero, but T of null space is just 0. And null space is T invariant. Let me write here T invariant. So there are various ways and things like that to check.
Am I one doubt, ma'am?
Yes, sir.
For what operator T is
Not T invariant.
For what operator T is trivial invariant subspace? T as invariant subspace.
You mean trivial invariant means only 0 is T invariant kind of thing?
For what operator T as trivial invariant subspaces?
You mean only 0 and V are subspaces? I mean, your triviality, what is the whose triviality we are talking about?
Yes,
About
0 and V only, yes.
So that is true for any linear transformation, right? For any linear transformation, 0 and V are T invariant. This was the first thing which we did here. 0 subspace and V are always T invariant subspace. This is true for any T linear operator. This is true.
My question is only possible operator.
Only possible operator.
Yes.
Okay. Okay. Then we can have this. I don't know whether I can able to make this or not. X comma, sorry, we can do this. Then only possible spaces are either of this or this form. Not only this, but okay. Then these two are not T invariant, but we can have this. No, we are on field. I mean, I don't know. At this moment, I don't know any such example where only two are possible. Sorry.
Okay.
Yeah. I mean, because I started with this thinking that image of this will be y-axis and the image of this will be x-axis, but we can also have this subspace, right? For this set, x 1, 1. And this is T invariant under this map. So at this moment, I don't know any example. If I get to know, I will post it on the classroom, or we can discuss that in the next lecture. But at this moment, I don't know any such or if example where only possible are trivial subspaces. Okay. Any doubts now for this? Or anything related to what we discussed today?
No, clear, ma'am.
Okay. So I
Okay,
think we can
thank you.
start since we are over the time. Is it okay, right? Or if you have any doubts regarding anything, please let me know or we can end the session for today. If you have any doubts, please ask. Notes and video recording of this lecture will be available on the sheet which is shared with you by today evening around 8, 9. Okay, so I hope no doubts, then we can end the session here. Okay, thank you.
Okay, thank you.
Thank you.